Okay, so it's a great pleasure to have Zohar Komargodski from the Simon Center, and he'll talk about defects, renormalization, group flows, magnets, and Wilson lines, which is not the title that was initially announced. I guess Zohar, you'll explain.
Yeah, I'm
Thanks,
sorry
take
for
it
all
away.
those. Yes, thank you so much, first of all, for giving me this chance to present the subject. But originally, I promised to talk about some very exotic stuff that has to do with scattering of particles from monopoles and how it connects to the recent developments in generalized symmetries and such things. It's a subject that I've been discussing with David Tong and Kantaro Mori and Diego Del Mastro and Marieke van Beest, but we had to change that subject in the last moment because some little things there had to be fixed. So I'm gonna talk about a different subject today. So feel free to disconnect if you've already heard about this before. I'm gonna give some sort of summary that I prepared last night about what I've been doing in the last year and a half with many collaborators, and also many other groups in the world are working on related things. It's about defects in quantum field theory, which is the subject of non-local operators rather than local operators. How renormalization group flows are important for non-local operators. And I like this subject a lot because it really touches upon things that can be measured. And many of the things that I'm going to discuss today have complementary experimental verification by now, or Monte Carlo verification. So I'll give you applications of non-local operators in magnets. And finally, I'll talk a little bit about charge, what condensed matter people call charge impurities and we call Wilson lines, and renormalization group flows on Wilson lines from the point of view of non-local operators. And so that's the subject today. Maybe in the future, one of my collaborators can present the other subject of scattering from monopoles. Also, this is just I've been working on developing this subject for the last year and a half or so. We already have 4 papers out and a few more in preparation. I'll mention some results that are still unpublished in the course of this talk. So I'll start with some very gentle introduction, but please stop me for any questions and remarks. There might be lots of typos because I prepared this talk in a very rushed manner. So from the condensed matter point of view, the way conformal field theories arise, or critical points more generally, is that you go to 0 temperature. This is this horizontal axis at t equals 0, and you change some couplings in the Hamiltonian, and the Hamiltonian has various gapped phases, or maybe Nambu-Goldstone phases in various regimes, but then there could be a second order or even a higher order phase transition. And in many cases at this phase transition, there is an emergent light cone and there is a relativistic conformal field theory. So this is a very special point, which is a quantum critical point, and it has implications for the finite temperature phase diagram of the model. And so this is a vast subject that took off in the late 90s. Now, from the point of view of statistical systems, we also encounter conformal field theories. So these subjects nicely merged. And a lot is known about local operators and their correlation functions. So we know that local operators are in some representations of the conformal symmetry, and there are thousands of papers on constraints on correlation functions of local operators and their scaling dimensions and spin. But I think very little is known about the line operators in conformal field theories. So from the condensed matter point of view, you should think about the time slice. And a line operator looks like a point like impurity in a time slice. So you can think about it as modifying the Hamiltonian. I'll give some examples later. From the QFT point of view, where space-time is unified, it's just an extended operator. So what could be let's say that we fix the bulk theory to be a conformal field theory. So we're at a critical point and we insert some impurity. So from the condensed matter point of view or from the Hamiltonian point of view, when we take a time slice, there are basically two scenarios which must be contemplated. So one scenario is that the infrared, the impurity is completely screened. Completely screened means that if you go to the long distance limit, correlation functions do not see an impurity anywhere in space. The other scenario is that the impurity becomes a conformal impurity. A conformal impurity means that correlation functions are not the same as the ordinary conformal filter correlation functions, but there are various correlation functions that have algebraically decaying terms that see the impurity. So we will say that the line operator or a line defect is completely screened if it's basically the unit operator at long distances, and it's completely transparent to all bulk correlation functions. Now, there is another scenario that's actually important in the Kondo effect and some examples that I'm not going to discuss today. And that's where the impurity becomes topological, so its location doesn't matter, but still some extended other operators could see it. And this requires a d-2 form symmetry because you need the topological line in the theory for that to be even possible. You need a d-2 form symmetry. But the examples I'll talk today are like ordinary magnets and QED. And this is not, such a symmetry is not present in those examples. So this is not going to be a relevant scenario for the discussion today, but it must be kept in mind that this is actually important in some other examples, and in particular in the Kondo model. So we have two scenarios to discuss for today, whether the line operator is screened or whether the line operator is conformal. Now, historically, the study of such line operators was very important. I think Wilson actually discovered the renormalization group by studying the infrared limit of some line operators in 1+1 dimensions. This also was the first example, I think, or among the first, of integrability in quantum filtering. Conformal symmetry was discovered from the infrared limit of line operators, or conformal symmetry made prominent. But very little is known beyond 2 dimensions. So today's talk is basically about what do we know about conformal versus non-conformal versus trivial line operators in dimensions higher than 2. And this subject touches upon generalized symmetries because some line operators are protected by generalized symmetries, and I'm going to talk about it. And it's also a general subject about dynamics. It's often a dynamical question, whether a line operator is conformal or trivial. So just as a final picture, in condensed matter, the impurity could be any piece of garbage at a given time slice. So the understanding of the space of conformal line operators is equivalent to the understanding of which pieces of garbage are interesting and which pieces of garbage are not interesting. So any piece of garbage, which is a localized piece of garbage, is described by a line operator. And some of them are going to be trivial in the infrared, some are not. And this is the central question that one would like to understand. And the tools that we have are general constraints from the renormalization group and generalized symmetries. Are there any questions about this very broad introduction to the subject? Okay. So there are many familiar constructions in the literature of line defects. So in the high energy community, Wilson and Hooft loops are very famous. Those correspond to localized impurities which have electric or magnetic charge. In the condensed matter community, SPT defects, they are generalizations of the Kondo defect. I'll give you some examples later. Twist defects are important pseudo-line operators. Of course, if you study topological filters, anyons are line operators. And pinning field defects. I'll talk about this a little bit later. These are the most experimentally easily accessible. And I'll talk about what's known about the pinning field defects in higher dimensions. And there are many other examples of canonical constructions of line operators. So I'll talk a little bit, there is a missing bullet point here. I'll talk about general constraints from our G-flows. Then I'll talk about general constraints from generalized symmetries. Then I'll talk about examples in magnets, which are pinning field defects, then Kondo-like defects, which are called spin impurities. And finally, I'll talk about Wilson lines At the very end, if I have some comment, if I have time, I'll tell you about how S duality actually works in n=4 super Yang-Mills, which is not the standard story that you might have learned. Okay, so this is the outline, and now I'll get into a little bit more detail. So if you have a conformal field theory and you place a straight line somewhere in space-time, as I said, the straight line can be conformal or non-conformal. There might be an RG flow on this line, even though there is no RG flow in the bulk. But if the line is conformal, it's going to preserve a subgroup of the conformal symmetry in the bulk. And the subgroup, most importantly, contains an SL2R. And this SL2R acts on the line operator by Mobius transformations. So T goes to AT plus B over CT plus D, with this usual constraint AD minus BC equals 1. But if your line operator has not yet settled at a fixed point, then the symmetry is just translational symmetry and perhaps the transverse rotations like here. So a point like impurity in general, when you just insert it at a critical point, is not going to be conformal. So there will be some RG flow. And at the end of the day, there will be SL2R symmetry at the infrared. And the question is whether this fixed point is trivial or not as an impurity fixed point. Now, the space of operators that acts in the presence of an impurity is not identical to the usual space of operators that we have in conformal field theory. So we know a lot about local operators in conformal field theory, but now, due to the impurity or the line operators, or the line operator, some operators can be localized to the defect. And the space of defect operators is not related in any simple way to the space of bulk operators. There is some kind of connection between the space of defect operators and bulk operators. So let me denote defect operators by O hat and bulk operators by O. So we know a lot about the space of bulk operators. And in the presence of an impurity or a line operator, we can expand them in powers of the transverse distance from the line. And this is called the bulk defect OP. So we can expand bulk operators in terms of defect operators, but we cannot do the opposite. There could be many defect operators that don't have a sensible expansion in terms of bulk operators. So it's only one-sided, it's one-directional. And it's, as usual, it's useful at short distances from the defect. And as far as measurements go, what condensed matter people usually measure, or what's usually measured in Monte Carlo, is a particular term in the right-hand side of this equation, which corresponds to the unit defect operator. So the unit defect operator leads to a one-point function, which decays algebraically as you...
Zohar, I have a question.
Hi, Hiroshi.
Hi, I have a question. So you said that this relation is in one direction, but then what does this equation mean?
It means that if you take a bulk operator, you can expand it in terms of defect operators.
But you cannot express bulk operator, obviously, in terms of superposition of defect operators. That's what you meant by one-sided, is that right?
No, what I meant is that in any correlation function of bulk operators in the presence of a defect, you can reduce the problem of computing such correlation functions to computing some correlation functions of defect operators with some...
Okay, so when the bulk operator is near the line, so you can replace bulk operator in the correlation function by the linear combination on the right-hand side. Is that what this equation means?
Yes, 100%. But,
okay,
in some sense, intuitively, there could be many more O hats than O's, because there could be an enriched Hilbert space at the impurity. So one of the famous examples that I'll talk about is when the impurity has many degrees of freedom localized to that point. So the bulk spins could be spin half qubits, which are tuned to some fixed point, but at the red point, there could be spin S qubit, with S being 100. So clearly, there are many operators that only act on the Hilbert space of the red point, but they cannot be somehow sensibly moved out of the red point. They only exist at the red point.
Okay.
So operators that act on the blue points can be expanded in terms of operators that act on the red point. but operators that can act on the red point cannot be expanded in terms of operators that act
Oh,
on the
that's what you meant by one-sided. Yeah, I was confused what you meant by one-sided. Thank you. Thank you
Yes.
for clarifying.
It's not a map. There is no map. It's just that you can bring operators that act on the ordinary spins to the defect spins, but you cannot do the converse.
Right. Thank you. Thank you for clarifying.
Yes, thank you. And the most important observable that we have a lot of data about from experiments and Monte Carlo simulations is the one-point function of bulk operators. Clearly, it decays algebraically as you go further away from the defect, but this coefficient is important. It's a physical coefficient that is measurable, and that's what we have data about. So we say that an impurity is not screened if this coefficient is non-vanishing for many or most or some bulk operators. But if for all bulk operators this coefficient vanishes, one can probably prove a theorem that the whole defect is completely trivial. This was not proven, but I believe it's true. So if there are no bulk one-point functions, the whole defect should be trivial, presumably. So therefore, this is like the key observable in some sense.
It could still have some sort of, localized topological degrees of freedom, probably.
Yes, that's the reservation that I made a reservation about it here.
Mm-hmm.
Indeed, if you have an impurity that in the infrared becomes topological impurity, so no local operator is gonna see it. And then all these coefficients A gonna vanish. But this requires the system to have topological impurities, which means a D-2 form symmetry. And I'm not gonna discuss such theories today. So therefore this conjecture makes sense. To make it more concrete, this conjecture, what I really want to say is that if all the A's vanish for all bulk operators, you can probably prove that the displacement operator vanishes. So every defect has an operator that lives on the defect, which allows to displace the location of the defect. Just move the defect to a nearby point. It's called the displacement operator. And if there is an operator equation, which is that the displacement operator vanishes, that means that the defect is either topological or completely screened. So I would like to prove a theorem that if all the A's vanish, then the displacement operator vanishes, but I don't know if such a thing was proven. I think Yifan Wang and collaborators have some paper that they're writing proving that for the energy momentum tensor in the bulk, this coefficient has to be non-negative. But I don't know if they prove that if it's actually vanishing, the whole thing is trivial. I'm not aware of that statement. Okay, so this is what's measurable. Now, what are the general constraints? First, I'll tell you about the notion of a defect entropy, which generalizes the quantum dimension for the topological case. So let me just quickly tell you what's the idea. If you take a line operator and you go to Euclidean signature, you can make it into a circle and you can compute its partition function. This is a very famous operation in topological field theories. It computes the quantum dimension of the corresponding line operator. You can do it in any theory, not just topological theory. It's just that it might depend on the radius. So this defines the defect entropy, which is a function of the radius. So you take the expectation value, or more precisely, the logarithm of the expectation value of the circle. You need to apply a weird operator that depends on the radius of the circle, and that defines some radius-dependent defect entropy, which at the fixed point is the logarithm of G by definition, which is the quantum dimension of the conformal defect. So the reason that you have to apply this weird operator is because such a partition function may have divergences. It's the same in Chern-Simons theory, by the way. We must make a subtraction due to the linear divergence on the line operator. So we can define the analog of a quantum dimension for any line operator in conformal field theory, and it becomes a function of the radius of the line. And this function is interesting because it sort of tracks the RG flow. So for very large R, it's like you're in the infrared, and for very small R, it's like the UV. Now, this defect entropy is a completely scheme-independent observable. And at the fixed points of this line operator, we can call it the quantum dimension. Of course, it's very difficult to measure it because condensed matter, people cannot make space into Euclidean and take a line operator to be a circle. That doesn't make any sense, but it is defined as an observable. And one surprising thing is that you may remember that in topological quantum filters, there is a theorem that log G is positive, or the G is bigger than 1. But we will see that in conformal defects, that's not true. I'll give you many examples of conformal impurities where the quantum dimension is arbitrarily negative. And that's interesting because of the following intuitive picture. So what is the quantum dimension? In topological theories, the quantum dimension is like how many degrees of freedom there are at the line operator. But in a conformal field theory, there are degrees of freedom in the bulk, but also degrees of freedom on the line or on the impurity. So log G kind of measures what happens in the presence of the impurity. Does it push out bulk degrees of freedom or does it not push out bulk degrees of freedom? And so negative log G is sort of saying that the impurity effectively pushes out the degrees of freedom in the bulk. So that's why log G can be arbitrarily negative in conformal defects. Now, there are RG flows on line defects. They're given by just integrating defect operators. This is like standard RG flows also in ordinary conformal filters. We just integrate a local operator on the defect. And the defect entropy, as I said, is a non-trivial function of the radius. And as you go to the UV fixed point, it's the quantum dimension of the ultraviolet fixed point. When you go to infinite radius, it's the quantum dimension of the infrared fixed point. And you have a nice function that tracks the RG flow. And one general theorem that you can prove, you can actually prove a sum rule. I'll tell you in a second what is the sum rule, but you can prove that the defect entropy is monotonically decreasing. And that proves that the quantum dimension cannot increase under RG flows. So the intuitive picture is that as the RG flow proceeds, degrees of freedom of the bulk are pushed out from the impurity. So the impurity can only push out degrees of freedom as the RG flow progresses. And there is actually a full-fledged sum rule for how the defect entropy evolves under changing the RG scale. And there is a sum rule that involves correlation functions of the energy density modulated by a weird positive definite kernel function. So it's manifestly negative. And it's a very general constraint that holds in magnets, in any condensed matter system. It holds in every number of dimensions, for impurities in every number of dimensions, that the quantum dimension is a monotonically decreasing function. And today I'll show you some very cool applications of that for magnets. Are there any questions? I'm not giving a proof, of course, but I'm just quoting the result. Any questions about this?
Yes, I have a question. If you take the limit of the line very small, this recovers kind of C theorem if you turn the line into a point.
Okay. Not sure that I didn't think about this perspective. So here we're just measuring the partition function of a circle, and we're asking how does it evolve as a function of the radius of the circle. And we think about it as interpolating between the quantum dimension of the ultraviolet fixed point and the quantum dimension of the infrared fixed point of the line operator. You are saying that maybe I can interpret it when the circle is very small as a local operator. So maybe this is something about the evolution of local operators. You're completely correct that a line operator that's a circle can be expanded in some infinite series of local operators, but I didn't think about this perspective and what does it teach us.
Mm-hmm.
So yeah, I don't have much to say about it.
Okay, thank you.
Now, in the context of 1+1, such a decrease of the quantum dimension, what is known from the Kondo effect, and it was conjectured by Affleck-Ludwig. It appeared in the context of string field theory, actually, at around the same time. And Friedan Konechny wrote a proof in 1+1 dimensions for this fact. So what I'm doing here is just a generalization to any dimension. This generalizes this theory of impurities to any dimensions. And one thing that's very annoying is that in 1+1 dimensions, log G has a beautiful interpretation using entanglement entropy. This was found by Cassini, Salazar Landea, and Toroba in 2016. So let me tell you what they did in D equals 2. It's only true in D equals 2. So in D equals 2, the quantum dimension, unfortunately, well, this observable is weird. We cannot measure it. But in D equals 2, there is a way to measure it directly. You can place the impurity at the center of a circle. Sorry, in 1 + 1, it should be an interval. So you can place the impurity at the center of an interval, compute the entanglement entropy of that interval, and the extra entanglement in the vacuum due to the impurity is equal to log G. This was proven by Cassini, Salazar Landea, and Toroba in 2016. So while you cannot measure log G directly from this partition function, you can measure the entanglement in the vacuum due to the impurity. However, it turns out that in higher dimensions, it's not true. So in higher dimensions, when you add an impurity, let's say inside the disk, you ask what is the added entanglement entropy in the disk. It's not log G. So there is no clear QI interpretation of what log G is at the moment. But there is a paper from just a few weeks ago, or maybe 1 month or something ago. No, it must be a little more. Anyway, there is a paper from a few months ago by, again, the same authors that proposed some new QI observable that would actually be equal to log G, also in D equals 2, in D equals 2 + 1, and in D equals 3 + 1. So a higher dimensional generalization. But yeah, it seems a little bit more complicated, so not easily measurable. Yet, as a theoretical device, it's very useful because it provides a completely general constraint on our G flows that I'm going to use.
In higher dimensions, can you show something similar for not line operators, but surfaces or higher dimensional?
Yes, I was going,
Mhm.
right, I was going to skip all that discussion, but yes, you can do a lot of what I'm saying for surface operators.
And the question is then, do you have sort of, if you go to 3 dimensions, then for surfaces, you have some entanglement interpretation?
Oh,
I don't know, is this sort of a dimensional thing, or is
yeah,
it
it's
more
I don't
related?
know if I don't know if this is already known. As a RG question, certainly I can repeat this talk for surfaces. It's just that I have less experimentally verified results at the moment, so I prefer to focus on point-like impurities or like line operators. But
I
yeah,
mean, specifically in this context of the entanglement entropy.
yeah, I'm not sure about that. I'm not sure if some entanglement entropy is already known to exactly capture the effective number of degrees of freedom of the surface. I'm not sure about that. I feel that yes, but I'm not 100% sure. Okay. Okay, so this is a completely general RG constraint that's valid in any dimension, and you'll see some, I think, very nice applications to magnets. Another completely general constraint comes from extended symmetries. So we learned in recent years that line operators are charged under one-form symmetries. So an interesting question you can ask is, suppose we have a charged line operator, like a Wilson line in some gauge theory, conformal gauge theory with a one-form symmetry. Can we prove that that line operator cannot be trivial in the infrared? So it's an interesting question. And you can prove the following fact. You can prove that if the corresponding gauge theory, or if the corresponding theory that has a one-form symmetry does not have D-2 form symmetries, so suppose it doesn't have a D-2 form symmetry, that in 3 + 1 dimensions would be a 2-form symmetry. So suppose there is no 2-form symmetry, then you can actually prove mathematically that the Wilson line or the corresponding line operator cannot flow to a trivial line operator, and it cannot flow to a topological line operator. So one-form symmetry is very useful. As soon as you know that there is no D-2 form symmetry, a charged line operator must remain non-trivial in the long distance limit. So let me just give you a sketch of the proof. Let's think about L as our line operator, and let's think about this other circle here as the one-form symmetry surface. So if a line operator is charged, then so if the line operator is charged, it cannot be completely trivial, of course, because it's since some other surfaces must be able to see it. But you must rule out that it's just a topological line. But if it was a topological line, it would generate a D-2 form symmetry. And if you assume that this is absent, you therefore arrive at the conclusion that there must be a non-trivial displacement operator. So this is especially useful in 4 dimensions, but in 2+1 dimensions. So this is especially useful in 3+1 because 2 form symmetries are rare. But in 2+1, it seems a little bit less useful because 1 form symmetries are commonplace. But in 2+1, there is a version of this theorem which states the following. So if there is a 1 form symmetry that doesn't have an anomaly, then you can still prove that your line operator flows to a non-trivial conformal impurity. So roughly speaking, if you don't want to get into all these sub cases, you can think that the line operator that is charged under 1 form symmetry cannot be completely screened. That's a takeaway message that is kind of obvious.
Sorry, what it has to do with whether 1 form symmetry surface can be cut open or not?
So, so let's say that this is the 1 form symmetry surface. If it can be cut open, that means that you can somehow make it an open surface. So in general, when you have let me just go back a few steps. It's a lot of information packed into one slide. So sometimes line operators or surface operators can or cannot be cut open. So typically, when you cannot cut open a surface, it means that it's charged under some codimension P form symmetry. Because think about a line operator that is charged under 1 form symmetry. If it can be cut open, you'll reach a contradiction. So let's suppose that L can be cut open. Then you would reach a contradiction because you could take the 1 form symmetry surface through the cut and get.
Sorry, I thought L was a charged line.
Right. I'm just saying that I'm just trying to say it so you can think about it either way. It's kind of the same. So let's suppose this surface, which is the 1 form symmetry surface, can be cut open. Then you could drag it away without paying a penalty if you just drag it through the opening. On the other hand, if you drag it away in a way that cuts the Wilson line, you'll pay a price, you'll pay some phase. And in this way, you can reach some contradictions, or which is what I've been using when I made this statement. So you can actually prove that if it can be cut open, then the line operator cannot be a topological line. It must be an actual line conformal impurity with a displacement operator. It's maybe a slightly convoluted statement, but it's still very useful. You'll see that if I get to it, you'll see that in non-abelian super-Yang-Mills theory, this leads to pretty interesting conclusions about S-duality. Okay, are there any questions about this?
Sorry, could I ask? So if I have a conformal line and a 1 form symmetry, can the 1 form symmetry act on the defect operators of the line?
I would say we usually think about the 1 form symmetry as acting on the line. So it leads to word identities for correlation functions of insertions of the line operator. I don't know if there is a sense in which it can act on defect operators. I don't think there is. I'm not aware of such a thing. It seems to me that it's clearly not possible in any conventional sense because you can just move the line operator away from where there are defect operators without paying any price. So yes.
So I have a couple of questions. So are you allowing for the possibility of it flowing to zero line?
Flowing to zero means
that-
flowing to a trivial point.
So for it to become confined.
There's no my theory in the bulk is a conformal field theory. So a confined line, I don't know what it would mean. There's no such thing. A line operator in a conformal field theory has two possible fates. One, it becomes the unit operator. The other is that it becomes a conformal line operator. Going to zero is not a possible fate. It requires a scale that is not possible, namely the string tension. Lines in conformal field theory always have zero string tension. But that doesn't mean that they are trivial. They could either be non-trivial conformal line operators, or they could be trivial conformal line operators, but they always have zero tension.
So in both of these statements, there is this assumption that the bulk theory is conformal.
Yes, this whole talk is only about that case.
Okay.
But there are many papers where they do. I'm always talking about this setup, you see. But there are many papers that kind of go beyond, right? Once you have understood the conformal point very well, you can go to finite temperature, you can try to deform, but it's always useful to start from the conformal point itself. And then you can try to go away.
Okay, thank you.
Okay, so if you look at the literature, there are many ways to construct non-trivial line operators. I'll just quickly go through them. One very easy way is that you start from actually the unit line operator in the ultraviolet and take a bulk operator and integrate it. So usually, so let me just explain this because I'm going to give you an example. This is probably the most famous, the most easily measurable cases. So you take a conformal field theory, which happens to have an operator of dimension smaller than 1. There are many such conformal field theories. And you integrate that operator, but instead of integrating it on the whole space, you integrate it just on a line at x equals to 0, say. What is the meaning of doing this thing? The meaning is that usually local operators couple to external fields like magnetic field, electric field. So the meaning of this operation is that we're turning on an external field, but only at a few lattice sites. So we are used to studying critical systems as a function of magnetic field or temperature, but we turn this temperature or magnetic field everywhere in space. This is not mandatory. We can turn the magnetic field or the electric field only at a few lattice sites. And that's achieved by integrating the local operator at a given lattice, at a given position in space. Condensed matter people call this kind of operation pinning field defect. You can also call it an external field defect because it corresponds to turning on an external field at a point. The virtue of this construction is that it has a zero quantum dimension in the ultraviolet, because in the ultraviolet, you haven't turned on any operator. So you just have a trivial line with zero quantum dimension. So this example is important. I'll give you one. I'll give you an of how it actually works. A more complicated example, which is a generalization of what I did just now, is to have a non-trivial quantum mechanics on that point in space, at that point in space. So there could be some quantum mechanical model living at that point in space with some quantum mechanics operators T, and then you could couple those T's to the bulk O's, to some bulk operators O. So now in the ultraviolet, the quantum dimension is non-zero because you have a non-trivial quantum mechanics at that point, which might have vacuum degeneracy. So for instance, you could take a qubit and couple it to some CFT. So this could be just an operator that's acting on qubits, which you can then couple to a CFT. Again, I'll give you an example of that. Another construction is much more famous in the high energy community is when we gauge a common symmetry. So we take a quantum mechanical model with a global symmetry G, which is gauged in the bulk, and we just gauge the diagonal. So that's how we get Wilson lines. So we just say that the quantum mechanical degrees of freedom are charged under the bulk gauge symmetry. That's another construction. And there are many others. You can do what's called the monodromy defect. I don't want to go into that because I'm not going to talk about it today. Now, dualities presumably interchange the descriptions above. So it's actually not known how boson fermion duality acts on these line operators. or even how mirror symmetry acts on these operators is not fully known. But probably these descriptions are interchanged. There is a lot of evidence for that. And I'll just give you some examples now of applications of all these ideas. Are there any questions before I jump into concrete examples? Okay, so the first example is of the first type. It's an external localized magnetic field in a magnet. So we start from the bulk conformal field theory, which is the ON model, about which a huge amount is known. It's the Wilson-Fisher fixed point. And we integrate the order parameter at the x equals to 0. I should have written phi 1t at x equals to 0. And SON stands for the critical bulk ON model, as I said. Now, here the G theorem has a far-reaching application, which I like. Because GUV here is 1, as I said, in the ultraviolet, the coupling H goes to 0, so the quantum dimension is vanishing. From the G theorem, we learned that the infrared quantum dimension cannot be bigger than 0 because it's a monotonically decreasing function. And that immediately says that the infrared cannot be screened. Just because we learned from the G theorem that log G in the infrared is negative, that immediately means that it cannot be screened. And in condensed matter, it was actually an open question of whether this kind of localized magnetic field is screened or not in the infrared. But we see that it cannot be screened. And now I'll show you evidence by concrete computations in the large N limit that indeed it is not screened in the infrared, and indeed it is obeying the G theorem, namely that log G is negative. So in this example, we get negative log G. As I promised, this is not possible in TQFTs, but in CFTs, it is perfectly possible. So people realize this kind of construction in Monte Carlo. There are many papers also from recently. And they see also numerically now that the infrared is a non-trivial defect conformal field theory. This stands for defect conformal field theory. So it's a conformal field theory with a conformal line operator. So what can you do with this if you want to solve this model, the ON with the localized magnetic field? Like, what can you possibly do? Of course, you can do an epsilon expansion because the coupling H is nearly marginal, I'm sorry. But you can actually solve the large N limit exactly. The solution of the large N limit is very cumbersome, but it is possible by finding a solution to the Schwinger-Dyson equations at large N. So I'm going to give you I'm going to quote a little bit the results from large N now and compare them with experiment. So if you compute the quantum dimension at large N, first it's in the epsilon expansion. If you compute the quantum dimension in the epsilon expansion, you see that it's slightly negative. As I promised, it has to be smaller than 0. And a very important defect operator is phi 1 hat, which is the order parameter brought close to the defect. And that picks up a positive anomalous dimension. You find something, roughly speaking, similar in large N. There are many papers about it, about this large N saddle point and variations of it for tensor models for SYK and so on. And you find a log G, which is arbitrarily negative. This is the large N limit result. Log G can be as negative as you like when N is very large. And the defect operator dimension is known analytically too. It picks up a huge positive anomalous dimension. So what is the bottom line of this example? The G theorem is obeyed. There is a non-trivial conformal line operator already in the Wilson-Fisher models, and it describes an external localized magnetic field. And if you look in experiments and Monte Carlo simulations, they're not yet precise. They have like a 10% error, but they find that the defect operator dimension is indeed 1.5, which roughly agrees with the large N computation. Probably there is very weak N dependence in these models. We looked at it a little bit in the epsilon expansion, where I quoted here. And actually this looks like a terrible function of N, but it actually doesn't vary very much from N equals 1 to N equals infinity. So it seems that there is very mild N dependence, and the large N result turns out to be very close to experiment. There are 3 experiments at the moment, and they all give answers between 1.45 and 1.55. So this is a nice conclusion for this simple case. Are there any questions about it? Now I'll give you an example where you do something a little more complicated. Okay, so now I'll give you an example where you do something a little bit more exotic. So this is as close as you can get to Wilson lines, but just with magnets. So what's the idea? The idea is, let's say for simplicity, we'll just look at the O3 Wilson-Fisher model, which is the ordinary magnet. And now we do what I showed you in this picture long time ago. We add a latticite with a spin s degree of freedom, where the bulk is spin 1/2. So I'm going to write a Lagrangian for this thing. It's an antiferromagnet. And the Lagrangian for this thing is that you take the O3 Wilson-Fisher fixed point, and you couple the order parameter in the bulk to the spin matrices. This is the spin matrices in the representation of spin little s. So you couple the order parameter to the spin matrices, and you call the coupling constant gamma. So this is a line operator which is non-abelian because the spin matrices don't commute, obviously. So this is like as close as you can come to a Wilson line just in the magnet. We have essentially a spin s representation that's fluctuating, and it's coupled to the bulk order parameter. And if you write it as a Wilson line or a line operator, you need pass ordering, you need trace, and you need some non-abelian matrices that couple to some scalar fields. This looks a lot like the half BPS Wilson line in n=4 super Yang-Mills that Hiroshi and many others studied. But this doesn't have the gauge field. It's only the scalar part. And otherwise, it looks pretty similar. But here, we don't have gauge fields neither in the bulk nor on the line. And it describes something that's very easy to cook in an experiment. So what can we say about the infrared limit of this line operator? So for the BPS line operator in n=4 super Yang-Mills, we knew that it's going to be a conformal line operator because of the one-form symmetry arguments. And people computed the large N predictions for its expectation values and log G. A lot is known. This thing turns out to be extremely difficult to obtain analytic results about because it's a line operator in the Wilson-Fisher fixed point. It's difficult to obtain analytic results. What's known at present is that there are some experiments for little s = 1/2, which is just a qubit. And also, we wrote a whole paper where we found an analytic solution of this model at large little s. So when the spin of this impurity is very large, it turns out that there is a new semi-classical limit, and it's solvable exactly. So from the study of the large little s limit, we generated a bunch of predictions. So that's what's been done on this subject for now. Of course, you can do epsilon expansion again, and there are many papers on this. And what we did is that we solved it even at d = 3, but at very large spin for the impurity. That's analogous to Wilson lines in a very large representation. And there are a bunch of papers on this recently. These are some authors. Okay, so what is the bottom line? The bottom line is that experiments for this model show that there is a fixed point even all the way to s = 1/2. That's the current state of the art. And in the large S limit, we showed analytically that there is a fixed point, and we computed some scaling dimensions analytically and so on. So it seems that in d = 3, this external spin model flows to a fixed point. And at present, there are some, as I said, experimental results at s = 1/2 and analytic results at large S. Okay, so this finishes the discussion of spin impurities. Now I want to get into the last 10 minutes. I want to tell you about Wilson lines, which is quite an interesting story also. Wilson lines.
Sorry,
yes.
Away from the defect, you have a spin half antiferromagnet? Or...
Yes. So in this construction, you can put any spin S at the defect with some particular couplings to the nearby spins. But away from the defect, you have spin 1/2 indeed.
Okay.
So if the defect is spin a half, it doesn't mean that it's just trivial, because it has different couplings to the bulk from the blue spins.
I see, right. And for any, all the way from large spin to down to spin a half, the defect flows to some non-trivial conformal defect in the IR.
That's it. So at spin a half, we only have experiment, and it seems that this is the case. For large S, we proved it analytically. And so it's reasonable to believe that for all little s, it flows to a conformal defect. A problem that is a baby version of this problem that you can say a little bit more about is when the bulk is the mean field O3 model rather than the interacting O3 model. And actually there it's a little bit, it's still not solvable. It's still a very difficult non-abelian line operator, but you can say a little bit more. So you can take a look at this literature that I cited if you wanted to, or send me an email about the mean field theory. This is the diagram of what's currently known for the interacting O3 magnet in the bulk.
And D equal to 2, I guess a lot must be known about the line defect.
You see in D equals 2, O3 doesn't have a second order transition. So you wouldn't do this thing in D equals 2. It's because the bulk is not at a critical point.
But in D equal to 2, if you have SU2 level 1 antiferromagnet, and
then of course you know a lot is known about this construction. Yes, then you couple SA to G-1 dg. And you get the Wilson line for G-1 dg, where G is the Wessel-Minowitten variable. And a lot is known about the fate in the infrared of that line. And actually, in many cases, it's not conformal. It flows to a topological line, which is a very Linde line operator. It's one of the topological lines in Wessel-Minowitten theory, which is a very Linde line. So the story in D equals 2 is quite different from what I'm saying here. Okay,
thanks.
So in D equals 2, roughly speaking, when the representation is very large, you get a conformal fixed point. When the representation is not very large, you get the Berlin topological line operator. Here, experiment and theory suggest that it's conformal for every spin. Now, let me finally talk a little bit about Wilson lines, which are probe particles, which may or may not be charged under one-form symmetry. So even Wilson lines, which are not charged under one-form symmetry, may turn out to be conformal line operators. The fact that there are matter particles in the bulk with the same representation does not mean that the Wilson line is going to be a trivial conformal fixed point in the infrared. So let me give you an example. This is a pedagogical example. We take just QED in 3+1 dimensions, just ordinary QED, gauge field coupled to a scalar field of charge 1. You might think everything is known about it, but you'll see that it's a little bit more complicated. So we just take ordinary QED in 3+1 dimensions with a scalar QED, ordinary scalar QED in 3+1 dimensions, and we have a Wilson line. This is how we represent an abelian Wilson line of charge Q. So the usual vacuum of QED is where the gauge field vanishes and the scalar field vanishes. But in the presence of a Wilson line, this is not the correct vacuum. The correct vacuum is what we learned in high school. It's a Coulomb field. And of course, well, there is a solution to the equations of motion where the scalar field vanishes. So you can say that's the end of the story. The infrared limit of the line operator, which is the Wilson line, is a Coulomb field and a vanishing scalar field. Unfortunately, or fortunately, this turns out to be wrong for the following reason. We can assume by contradiction that this is the right answer. That you can think about the Wilson line in scalar QED as a nucleus. So what happens to QED when you put an external nucleus of charge Q? You would say it just creates a Coulomb field. What is there to discuss? But if you assume that this is the right answer and you compute the scaling dimensions of some defect operators, in particular phi dagger phi, where the heads mean that it sits on the defect, you find a closed form formula in some scaling limit, some weak coupling limit, This is the scaling dimension of the bilinear phi dagger phi on the defect. This becomes imaginary when the charge of the nucleus is too large. In particular, if you plug real life values of the coupling constants, this was going to be like 68, 69. So when the charge of the nucleus is too large, it doesn't make sense to say that the nucleus creates a Coulomb field. So the infrared limit of that line operator, where the charge is bigger than e squared over 2 pi inverse, is not going to be a Coulomb field. This is some weird sickness of the QED vacuum to putting an external nucleus. But the physics is pretty clear. It's when the electric field is too large, you kind of destabilize the vacuum of QED because you have a very large electric field. So one could say that in some sense, Wilson was wrong. This was the formula of Wilson for the Wilson line. But he forgot to put the bilinear in phi, which becomes marginal or even relevant in some situations, like I said before. You see that the dimension of this bilinear is very close to 1 when the charge of the Wilson line is close to e squared over 2 pi inverse. So you could say that the Wilson line admits many marginal operators. This is not the same as the operator that appears in n equals 4. In n equals 4, to make the Wilson line BPS, we add a scalar field phi. But here, we must, even in a billion QED, we must add phi dagger phi to understand Wilson lines with arbitrary charge Q, because phi dagger phi becomes nearly marginal, and it has an RG flow. So if you omit this operator from the formula of the Wilson line, you make a mistake. You'll make a mistake. This is the beta function for this new coupling G. If the nucleus has a small charge, there are actually 2 fixed points. So there are 2 distinct conformal Wilson lines for small charge nuclei. As you increase the charge of the nucleus, the 2 fixed points meet. And as you increase it further, the 2 fixed points completely disappear. This phenomenon that as you increase the external charge, something bad happens to the vacuum was already seen in graphene in an experiment of Shitov et al. At MIT. In graphene, it's easier to see this phenomenon because the effective fine structure constant in graphene is not 68 or 137, it's actually 5 or 4. So this phenomenon that the external nucleus destabilizes the vacuum happens for much smaller nuclei. So we see that the formula of the Wilson line must be corrected in this way. And this is the beta function. We see that for small Q, the Wilson line has at least 2 fixed points. And then they annihilate into the complex plane. To understand what happens when you put a nucleus with a too large charge, so there is no more fixed point. So what would you say? What is the infrared limit of the Wilson line? There doesn't seem to be any fixed point. This reminds us probably of QCD, where the gauge coupling runs to infinity. Here also, this new coupling runs to infinity when the charge of the nucleus is too large. And there is actually dimensional transmutation on the line operator, and a new exponential scale is generated. So the dynamics of these line operators in gauge theory is very similar to how conformal symmetry is broken in QCD, and you have chiral symmetry breaking and this kind of stuff. And it's also very similar to the BKT transition. Sometimes people call it the Miransky scaling transition. So you generate a new exponentially large scale. This was not seen in an experiment, I believe, yet. You generate a new exponentially large scale from the RG flow on the line operator. And what actually happens is the following. So let me just give you a picture of what happens if you put a nucleus of charge 70 in the vacuum of QED, scalar QED. So at the beginning, the electric field is as if you have a nucleus of charge 70. But very quickly, a scalar condensate appears, and the electric field drops to 0, and the scalar field eventually drops to 0. So if you put a nucleus which has too high charge because of this running to infinity of some coupling constant on the Wilson line, you get complete screening. So the line operator is completely trivial in the infrared. And this happens over a huge distance scale, you see that it goes all the way to the moon just from a single nucleus. So this is a very nice example of a generation of an exponentially large scale from just one atom, one nucleus. So what is the bottom line? The bottom line is that in QED, the phase diagram of line operators is that for small enough charge, you have a conformal line operator, or actually a few of them. There are at least 2 fixed points. And as you increase the charge, they become screened. In this example, there was no one-form symmetry. So there was no obstruction for some line operators to be completely screened. But what if the elementary scalar field phi had charge too? Then there would be a one-form symmetry, and some line operators cannot be screened. So something about the story of this cloud cannot be right. If you take a Wilson line of charge 72, it cannot be completely screened because it has 71, because it has an odd charge, so it's charged under one-form symmetry. So actually, this is an open question. We don't know how to show that interiors with a one-form symmetry, this screening cloud has even charge. It's still an open question. And that's more or less what I wanted to say about the abelian QED.
Zohar, can I ask a question?
Yes.
So I would have expected that the charge screening stops when you hit the critical value. Why does it continue to screen it to 0 charge?
This is an excellent question. There is a big difference between putting a nucleus in a theory of bosons and a theory of fermions. In a theory of bosons, as soon as you create this instability for the coupling G, all the bosons rush in and kind of create a Bose-Einstein condensate, and they just don't stop. But in the theory of fermions, we have a lot of indications that what you said happens instead, that you create an instability, but as soon as a few fermions fill in that instability, you cannot put more fermions, and it just stops at the critical value.
Okay, thank you.
This is presumably also what happens in graphene. In graphene, if you put a slightly too large charge impurity, it should screen only to the critical impurity charge, not all the way to 0. But it should still generate an exponentially large scale. The exponentially large scale should be basically the same formula, like this, except that it would be 16 and not 4. So this is the story in abelian scalar QED, but it's exactly the same in n equals 4 super Yang-Mills. So even in n equals 4 super Yang-Mills, the non-supersymmetric Wilson line operators must be accompanied by this operator, and its RG flow determines the spectrum of non-supersymmetric Wilson lines. And this screening phenomenon happens even in n equals 4 super Yang-Mills. It's almost the same story. And it would be nice to see it in the ADS-CFT correspondence. It was not seen yet in the ADS-CFT correspondence. Okay, since I'm running out of time, I don't have much more time to talk about how this is compatible with S-duality. Because
I think you can take the time to talk about S-duality.
Okay, maybe I'll just say it in words. I don't want to annoy people with sitting here for too long, so let me just say it in words of what the conclusion is. Let me find the best slide. So we find here that as you keep increasing the representation or the charge, the Wilson lines are screened for a large charge. This is interesting in the context of S-duality, because that means that as you increase the coupling constant, or if you increase the charge, your Wilson lines are going to disappear. So if you study super Yang-Mills theory, for instance, it would mean that as you increase the coupling constant, all the Wilson lines will be completely screened, except for those that are charged under one-form symmetry. So let's say if you study SO3, super Yang-Mills theory, there is no electric one-form symmetry, and therefore at large coupling constant, there will be no Wilson lines. This is what this predicts. But this seems odd with S-duality, because S-duality predicts that Wilson lines at strong coupling are the same as 't Hooft lines at weak coupling. So this predicts a remarkable thing, that if you go to very weak coupling, SU2 super Yang-Mills theory, which is the dual of SO3 Yang-Mills, SU2 is the Langland's dual of SO3. So it makes a remarkable prediction that there are no 't Hooft lines at weak coupling, no conformal 't Hooft lines at weak coupling. And some preliminary study seems to be indicate that this is indeed correct. So we try to study 't Hooft lines, that's very weak coupling, and we don't find any stable saddle point. So to say that the 't Hooft line creates a magnetic field seems to be wrong. The magnetic field, even if it's even if the coupling is very weak, seems to completely destabilize the vacuum. So preliminarily, I think that the story of S-duality is that, roughly speaking, there are no 't Hooft lines at weak coupling and no Wilson lines at strong coupling. And that's how S-duality is compatible with the spectrum of line operators. So thank you so much.
Okay, thanks a lot. Are there any more questions? Can I ask about this last statement you made? So how would this work in a holographic setting? I mean, there, of course, you're just going to strong couplings in SUN, and you have some center ZN one-form symmetry.
Yeah, so
and
actually,
you're saying then you should actually see in the Wilson lines in the holographic description that there's this kind of additional coupling, not just this sort of supersymmetric version of the Wilson line, but also phi dagger phi coupling. This is what you were saying essentially. And
yes,
phi here is like the adjoint scalar field. Is this what you're proposing?
yes, it's certainly true what I'm saying, that if you look at SO6 being the R symmetry, if you look at SO6 invariant Wilson lines in n equals 4 super Young Mills, certainly you must add phi dagger phi for large enough representations. And the running of that operator will destabilize all the line operators at strong coupling, or all the line operators at sufficiently large representations.
And you should see this from the supergravity dual description in terms of those.
Yes, that should be possible. We have not tried yet, but for SU2 and SO3, I know the story in more detail, so I can say it quickly.
Yeah.
For SU2, of course, at strong coupling, there will be one Wilson line, which is not screened because we have a one-form symmetry, and the one-form symmetry can be cut open. So it passes the criteria that I explained at the beginning. So at SU2, in SU2 gauge theory, there is exactly one Wilson line at strong coupling. This suggests that when you go to SO3 gauge theory, there is exactly one 't Hooft line at weak coupling, and all the rest are screened. And remarkably, this is easy to check because it's just weak coupling. And remarkably, when we looked at 't Hooft lines at weak coupling in SO3 gauge theory, there is exactly one. All the rest are completely screened by some instability of the vacuum. And in contrast, when you start from SO3 gauge theory, there is no one-form electric symmetry. So all the Wilson lines are screened at strong coupling, and that predicts that there are no 't Hooft lines in SU2 at weak coupling. And indeed, this is true. All of them are screened at weak coupling. So we find, I think, very clear evidence that this picture is indeed correct. And that's how S-duality works. At least for SU2 and SO3, everything is completely consistent.
Oh, very interesting.
Can I ask a question?
Yes, Hiroshi.
Yeah, so so when Sakura asked you a question about the higher dimension generalization of some of the property of the G function you talked about, you said many can be generalized to higher dimension. It's a little bit awkward to mention, but we had a seminar by one of your collaborators, and she told us totally opposite opinion that many of things won't generalize easily. And so, for example, what do you think would be the generalization of this derivative operator 1 minus R del del R, which used to render the function to be scheme independent?
Right. So I'm sorry that I portrayed an apparent discrepancy. So this does not have a generalization to higher dimensions. There is no monotonically decreasing function for dimension 2 defects. Not only, it's not because we didn't find one, it's more like people have systematically scanned over all the possible differential operators that would act on the expectation value and checked if one of them is monotonic, and the answer is no. It just doesn't seem to work. But though we don't have a monotonic function, for the endpoints, it can still be proven that this is true.
Oh, yeah, that's right. Yeah, that's what we heard too. So there is no monotonically decreasing function one that have not been found, I should say. Yes.
Yes. So a monotonically decreasing function has not been found, and there are several papers, not by me or my collaborator, scanning over possible monotonically decreasing function, and they haven't found one. But the endpoints always satisfy this, and this is proven.
Right. So at the end point, I guess the derivative vanishes. So it doesn't matter.
Yes, you're completely right.
Mhm.
So that is the status of dimension 2 defects.
Thank you. Are there anything else that generalized to higher dimensions? Or you are referring, so when you said it generalized to higher dimension in response to Sakura's comment, you are referring to this inequality.
Yes, but also some connections with the entanglement entropy, I believe.
Okay.
I
see.
believe.
So this one is not the same as previous one, but this one generalized to higher dimension. And does this have monotonicity?
Which one?
The one that these authors, Cassini and collaborators defined.
The one from 22?
Yes.
The purpose of their paper from recently is to find an entanglement entropy quantity, which literally is equal to G.
Okay. And is that monotonic or it is not monotonic?
They claim that it is, but their construction of the QI quantity that is actually equal to G is, I was not able to understand it completely.
Okay.
It involves an entanglement entropy with some infinite boost. So I couldn't understand what does it actually mean.
Thank you.
Yeah, so for these dimension 2 defects, there is a lot of work that I mean, I should have mentioned it at some point, but there are some experiments now going on about these dimension 2 defects that maybe my collaborator spoke about. I don't know, but yeah, you can say a little bit less about those things. There are a little bit less concrete results. Okay.
Okay, David, did you have a question?
Yeah, can I ask you about the graphene experiment, Zohar? I think you partially answered this in response to another question, but they're the screening fields of the gapless fermions.
Yes.
And what happens exactly? You put in some defect charge, and what's seen in the experiments?
What's seen in the experiment is that there is a condensate of the fermions that forms, analogous to this condensate.
Not a charge condensate, a psi with charge 2.
No. It's not a superconducting instability. It's a condensate that leads to electric charge. So you do not. So it's not a superconducting instability. It's a charge instability. Maybe that's what you said, and I said no prematurely.
No, I think you were right to correct me.
So what condenses is psi dagger psi. So they basically see, I think, this, but with phi replaced by psi. They see a condensate of psi dagger psi that like surrounds this nucleus that you put in, and that the effective charge is reduced. And I don't think that they can see the exponential scale yet, because that requires a little bit more delicate game with how much exact charge you put.
And is it different from usual screening in a metal?
It's very different, because in the metal you have Friedel oscillations. In the metal,
you don't have a Fermi surface. That's the point. You're at zero chemical potential.
A metal is another example where you can apply many of these ideas. But if you put an impurity in a metal, there is no actual exponent. There is no actual screening, because there are oscillations that go on forever.
But there's a power law envelope to these oscillations.
Yes, it decays like a power law, but there are oscillations. Here, what you see is that if you go to sufficiently far away distances, the effective charge in an envelope goes to 0. There are no oscillations. So it's a different profile, but of course, qualitatively, it's very similar. It's due to the subtleties of massless quantum fields, that massless quantum fields can create these huge, condensates that screen the charge.
Thanks.
Actually, this wasn't done for Fermi surfaces. It's one of the things I've kind of wanted to do for the last couple of months, because Friedel oscillations are not derived in an ab initio way. So it would be nice to actually repeat this literal exercise for a Fermi surface coupled to a charged impurity, because the widespread claim in condensed matter is that it leads to Friedel oscillations, but is it really true? I don't know.
And they're seen. I don't know what do you mean by ab initio? There's certainly a calculation one can do to derive Friedel oscillations.
Yes, but it's not a controlled calculation. It's a one-loop calculation which resums bubble diagrams. Sorry, it resums this like it's like an exponentiation of the one-loop diagram.
Is that right? Not the way I did it, but okay.
I see. Well, we can talk about it offline.
Okay.
I can give you an argument why this cannot be the full story. But roughly speaking, you're right. It's very similar, presumably. Any other questions?
Yeah. Any other questions for Zohar?
Okay.
Kantar just showed his face very quickly.
Sorry, yeah. Just a naive question that are you saying that the standard theory of atom doesn't apply to lead?
The what?
Say some huge nucleus with a too huge charge.
What about it? Please say again, Kentaro. I didn't understand the question.
You said maybe I misunderstand, but
I think he was referring to like a Coulomb potential with electric charge more than 100 to 27.
Yeah.
Yes.
Oh,
yes.
electric charge. Yeah.
Yeah.
Is it not the lead atom is beyond above the threshold you told?
Yes. If you try to, basically what I'm saying here is that if you try to solve the Dirac equation around the nucleus with charge bigger than 137, you'll find various instabilities, unstable modes. Massless Dirac equation. You'll find unstable modes, and those unstable modes would lead to a condensate of psi dagger psi. And so the treatment of the nucleus is not correct. It's not self-consistent.
Yeah, it's in one of the exercise of Landau-Lifshitz quantum mechanics.
I see.
Yes.
Yeah. But it doesn't.
The thing that this thing is classic. The thing that wasn't known is that, first of all, there are, for a similar reason, there are two fixed points for smaller charge, and there is a logarithmic running. This was not seen in an experiment, and it wasn't known. The second thing is that there is a phase transition, which is infinite order as you cross 137.
Oh yeah, sorry, I misunderstood. Yeah, okay. So that charge is above the like any stable nucleus. So
so the new results in that business is the first, as I said, there is two fixed points for a nucleus. So there are two things.
Yes.
And it's actually not clearly stated when we say a nucleus, what do we mean? Because there are two versions of what you might call a fixed point of the like a Coulomb field of a nucleus. There is an infinite order phase transition, and finally there is an exponentially large scale in the cloud. These results are not in Landau-Lifshitz, and they're much more recent. All of those. But
the two, okay. Yeah, between the two fixed points, one is IR and one is UV, right? So it's more likely that the actual atom is at the D.
Yes, so when we prepare a nucleus, it's going to be somewhere in between, presumably. And there's going to be some slow logarithmic running, and this was not observed yet, not even in graphene.
I see. Thanks.
Vladimir, you have a question?
May I ask a last question from the...
Yes, go ahead.
Yeah. So may I ask about your last comment about the lines in N equals 4 super-Young mills? Does that statement depend on whether you require the line to be BPS with some amount of supersymmetry, or it's
What I said only is relevant for the SO6 invariant lines, not to the ones of that are BPS that preserve SO5 instead rather than SO6.
I see.
So the puzzle here was to understand how S duality acts on the SO6 invariant lines. On the BPS lines, we know how S duality acts from localization. But on the SO6 invariant lines, the story is different. And as I said, roughly speaking, the picture is that at weak coupling, there are no 't Hooft lines whatsoever, unlike what you might have thought. But there are also no weak Wilson lines at strong coupling because of this instability. So it's compatible.
Okay, I see. Thanks.
Okay. I think we've exhausted all our questions. It was a very interesting talk. I'll stop the recording now.
Thank you so much.
Let's thank Zohar again for this very nice talk.